So the problem here is we are given two blocks, capital M and little m is dangling a distance h off the ground. And we need to find the velocity of the blocks just before it hits the ground. So we can use the energy theorem for this. And we can see here that this little block, lowercase m, is dangling distance h from above the ground. So this gives us potential energy. And we don't see any other forms of energy being put into this system here. So the kinetic energy and friction must add up to that potential energy in the end. And we can see it here, mgh with little m is equal to the heat generated by friction plus the kinetic energy of the whole system. And if we write it out a little bit more over here, we can see that the potential energy is equal to mu mgh plus 1/2 mass of the system, v squared. And you might be wondering, how did you get this? So we know that the force of friction is mu times the normal force. And the only thing that's experiencing friction right now is the block, capital M. So therefore, frictional force is mu m g f. And you're wondering where we get this h. So the work done by friction, the thermal energy released, is force times distance. And the only amount of distance that you can travel in this instance is h. So the thermal energy would be force of friction times distance. But since distance, the only distance that we can travel is h, would be force of friction times h. And that's how we got that little thing inside there. Now for kinetic friction, it's 1/2 mv squared, but we need to take into account both m's in this system because they move as one. And just to clarify, this question asks the velocity just before it hits the ground. And we don't have any sort of indicator of time or anything, but that's okay, because just before it hits the ground, that means all of the potential energy has been transformed into kinetic energy. So that means once this block has moved this distance h, and this block has moved this distance h, all of the potential energy from lowercase mgh has been transferred into velocity and thermal energy. So after we get to here, we can just solve for v. So that'd be mgh minus mu k capital mgh equal to 1/2 big M plus little m v squared. If we keep going, 2 mgh minus mu k mgh is equal to m plus little m v squared. 2 mgh minus mu k big M gh over big M plus little m equals v squared. And because I'm lazy, I'm just gonna copy, paste, and we just got to square root both sides, and we end up with this.